Hello and welcome to the next video for Chapter 12, Section 1. In this one, we're talking about more fundamentals of graphs, and in particular, a way to get a matrix from a graph. So after this, you'll be able to produce a matrix from a graph and be able to take a matrix and produce a graph out of it, so long as it's the right kind of matrix. In general, there's a lot of different ways to form a matrix from a graph. In this one, and in this class, we'll only talk about one way, and that's the adjacency matrix. All right, so what is an adjacency matrix? So that means we're going to take a graph and produce a matrix somehow from it. So I'm going to draw a graph over here. I like using this one for examples. This one's nice. I'm going to label these 1, 2, 3, and 4 will be my vertex set. And the idea is, so we're going to do this on small graphs, but really the benefit of being able to produce a matrix from a graph is being able to work to use linear algebra to operate on my graph. So there's a whole field of graph theory called spectral graph theory, which deals with this concept of what information can I gain about a graph by looking at its adjacency matrix, by doing this operation, and in general doing any operation that takes a graph to a matrix. And this is really useful for really big graphs, because computers can handle very large matrices, but maybe it'll be harder for the computer to handle this very huge graph. And so being able to get a matrix is helpful for computation, and there's a lot of neat things that you can gain from looking at the matrix. So how do we do this? We want to produce a matrix out of this, and this is sort of the follow your nose type of thing here. We want to encode all of the information of this graph into a matrix. Well, what information does this graph have? Well, it has the vertices, and it has what is adjacent to what vertex is adjacent to one other vertex. So I'd like to encode that in a graph. So what I'll do here is I'll make my columns the vertices. Each column will represent a vertex, and as well as the rows. Each row will represent a vertex, and I'll use the same labels for the rows and columns as I do for the vertices. And so I'll draw my matrix looking like this, just like a table of values. Hopefully you've worked with matrices before. You might have to go check out a video and refresh your memory on how to multiply matrices, because that'll actually have some use in graph theory. Multiply matrices or raise matrices to a power, we'll deal with those sorts of things. So how do I fill out this matrix now? Well, I'm going to put a 1 in the cell ij if those two vertices are adjacent, and a 0 if they're not. So vertex 1, right, this is a simple graph, it doesn't have any loops, and so no vertex is adjacent to itself. So I'm going to put zeros along the diagonal. And then here we have vertex 1 is adjacent to vertex 2, and so I'm going to put a 1 there. And also, right, this is an undirected graph, and so 2 should be adjacent to 1. And so in general, any adjacency matrix of an undirected graph should be symmetric along the diagonal like this. 3 is not adjacent to 1, so I'll put a 0 there. 4 is not adjacent to 1. By the symmetry argument, we should have this. 1 and 3, 1 and 4 are not adjacent. 2 and 3 are adjacent. 2 and 4 are adjacent, so I'll put 1s there, and we should have 1s there by symmetry. 4 and 3, those are adjacent, and 3 and 4, those are adjacent. So this is the adjacency matrix of my graph here. And so we should also be able to go the other way. So if I give you a symmetric matrix with zeros along the diagonal, and every entry is either a 1 or a 0, then we can take that and we can make a graph out of that. So that'll just sort of be reversing this process here. So we're going to, in the next section, look at some operations. So we'll take a graph, convert it to a matrix, and raise this to different powers, and look at the entries of that and see how it relates back to the other graph. And so it'll actually tell us some information about the graph. So that is doing operations on my matrices, multiplying matrices. These will have impacts on the graphs that they came from. We'll be able to obtain information from those. So let's look at one example of taking a matrix and turning it into a graph. So undoing this process. So I'll start with a matrix now. Let's say we have the matrix. It'll be let's do a 4 by 4 again. And let's say it goes, so it has to have zeros along the diagonal, otherwise it's not going to make sense. It won't be the adjacency matrix of any graph, but if it has zeros along the diagonal and it's symmetric and every entry is a 0 or a 1, then it is the adjacency matrix of some graph. So what I'll do here is I'll make 1, 1, 1, 1, 1, 1, and how about I let all these other ones be zeros. So here's a matrix. Let's see what graph it represents. So I'm going to go ahead and label, I don't know, maybe I'll use A, B, and C, A, B, C, and D for my vertices. So I'll label my rows and my columns with that, and then I'll draw those vertices, A, B, C, D, A, B, C, and D, and then I'll look at the matrix, which will tell me how to get edges here. So vertex A is adjacent to vertex B because there's a 1 in that cell. A is adjacent to C, and A is adjacent to D. And then we can see B is not adjacent to C, nor is it adjacent to D. C is not adjacent to B, C, or D. C and D is not adjacent. D is just adjacent to A, not B, C, or D. And so this is my graph then that came out of this matrix. So we just use that encoding method to go the other way. All right, that's it for this video. We'll talk more about adjacency matrices later on in the next section, but that's it for now.